To increase the frequency from 100 hertz to 400 hertz, the tension in the string has to be changed by how much? By what margin? I repeat the question. To increase the frequency from 100 hertz to 400 hertz, the tension in the string has to be changed by, there are possible answers. A, 4 times. A, 4 times. B, 16 times. C, 20 times. And D, none of this. Start work. I want to see what you can do within, okay, the time, about 5 minutes. A string of 7-meter length has a mass of 0.035 kilogram. So the mass is 0.035 kilogram. The length of the string is 7 meters. So a string of 7-meter length has a mass of 0.035 kilogram. If tension in the string is 60.5 Newton, if tension in the string is 60.5 Newton, then speed of a wave on the string is equal to, or what is the speed of the wave on the string? A string of length 7 meters has a mass of 0.035 kilogram. If tension in the string is 60.5 Newton, then the speed of the wave on the string is, so that's it. A string of length 7 meters has a mass of 0.035 kilogram. If the tension in the string is 60.5, then what is the speed of? Okay, so the answers are 77, B 102, C 110, and D 165. So we are also told that the tension is 60.5 Newton. Okay. Now velocity of wave is equal to velocity of transverse wave in a string is equal to square root of the tension divided by the linear density. The linear density. Okay. And linear density is also equal to mass per unit length. So when we find mu, this is 0.035 over a length of 7. Please divide that and then give me the answer. 0.035 divided by 7. So when we substitute that here, we'll have the tension 60.5 times 7 divided by 0.035. Okay. Or you can separately determine this and divide by T. Both situations will give you the same result. So 60.5 times 7, which is this, divided by 0.035. 035. That is giving us 12,100. So this is giving us square root of 12,100. Therefore, when we take the square root of our answer, we have 110 meter per second. So Ekweabuatuma got it right. Who else had it? Who else had 110? Adwa too had it. Okay. Nanama, are you there? So I have.
Yes, please.
Okay. All right. Last question on vibration in strengths. Then we move on to. So listen to the last question. In order to double the frequency, let me also discuss with you the plan B for the same question. For the same question, you see, velocity of sound is also equal to F times wavelength. The frequency times wavelength. Let me clear the same question. Okay, now let me. Where is the question? Okay, a string of length has a mass of this. If the tension in the string is, then okay, here it cannot work because we were not giving the as to whether it is the first harmonic. Okay, we would have used, assuming if it's that we are asked to find the velocity and it's the first harmonic or the first loop, then L is equal to this is half lambda. So lambda in this case will be equal to 2L. Lambda is equal to 2L. Then using, if it's the first mode or harmonic or the first loop, then F will be equal to F1 1 on 2L times T on mu. So we'll use this to find F so that we substitute F in place of this. And this is also giving us the wavelength. But the challenge is that we are not told whether it is the first harmonic, second, or otherwise. So the best way out is what we've done. V is equal to that. Please, are we okay? But we can still check if we will get the same answer. If we get the same answer, then it means that this is the first harmonic or the first loop. So there's no harm in trying. F in this case will be called 1 over 2 times 7. But this is actually waste of time because we can get V straight away from here, either than finding F before. Okay, so I think the best way out is what we've done. T over mu. Okay. When we go through this, it's an unnecessary thing we are doing because this alone would give us V. All right. So in order to double the frequency of the fundamental notes, please listen. In order to double the frequency of the fundamental notes emitted by a stretched string, in order to double the frequency of the fundamental notes emitted by a stretched string, the length is reduced to 3/4 of the original length. In order to double the frequency of the fundamental notes emitted by a stretched string, the length is reduced to 3/4 of the original length, and the tension is changed, and the tension is changed. Full stop. Now the factor by which the tension is to be changed is I'm going over the question. In order to double the frequency of the fundamental notes emitted by a stretched string, the length is reduced to 3/4 of the original length. 3/4 of the original length, and the tension is changed. Now the factor by which the tension is to be changed is A, 3/8, B, 2/3, C, 8/9, and D, 9/4. A, 3/8, B, 2/3, C, 8/9, and D, 9/4.
Please,
I
didn't hear from emitted.
You didn't?
I only heard up to emitted.
So listen to that. In order to double the frequency of the fundamental notes, emitted by a stretched string, the length is reduced to 3/4 of the original length. The length is reduced to 3/4 of the original length. Okay, I think I can send it to the group. So okay, let me send the question rather. Okay, so I've sent it. I've sent it to the group. Akuya, I've sent it to you, and Inshira, I've also sent it to you. So in order to double the frequency of the fundamental note emitted by a stretched string, the length is reduced to 3/4 of the original length, and the tension is changed. The factor by which the tension is to be changed is A, 3/8, B, 2/3, C, 8/9, and D, 9/4. NSMQ. Your time is up. NSMQ. Nanama, what have you had?
Please, I'm not done. Oh.
Okay, hurry up. Adwa, Equia, the two Equias, Immaculate, Gerard, Inshira, Josephine. Josephine, where is Oye?
Yeah, she's not here.
Hey.
Okay.
Pardon?
She's not here.
Have you sent her a message?
Yes, please.
Finish. Nine on 4. Somebody is getting 9 on 4. Nanama, we shall see.
Sir,
Gerard,
my answer is no inside.
none of this.
Yes, sir. My answer is no.
Okay, we shall see if all the answers given are odd. Yes, more views. Hey, NSMQ, you are delaying. Equia Abwa Aduma. On it, baby. Adwa, Josephine, Inshira, Immaculate. You are still on it. Okay, time. Because of time, let's look at the question. In order to double the frequency of the fundamental notes emitted by a stress string, the length is reduced to 3/4 of the original length, and the tension is changed. So the factor by which the tension is to be changed is, so if we are doubling the fundamental notes, okay, the length is changed to 3/4 of the original length. Then by what factor should the tension also change in order to have this? So it's the same string. So all that we are varying is that frequency would vary, and we know frequency to be directly proportional to tension and inversely proportional to the length. Okay, so the length changes, tension changes, and then the frequency changes, meaning mu is constant because it's the same string. It's the same string, so mass per unit length is constant. So even if you use F is equal to 1 over fundamental node, so N is 1 on 2L, T on mu, okay, 2 will cancel out for two different situations. When the length changes, tension changes, frequency will change. So 2 will cancel and mu will cancel out. So all that we can say is that, okay, then let F be directly proportional to the square root of the tension and then inversely proportional to the length. So it means that F1 will be directly proportional to tension 1 over length 1. Then F2 must also be directly proportional to T2 divided by L2. Okay. Now we are interested in if F changes and the length changes, how much would T also change? So if we take a ratio of F2 on F1, we have root of T2 over L2 times L1 over root of T1. Therefore, we have F2 over F1 equal to L1 over L2 times the square root of T2 over T1. Okay, Immaculate, please mute yourself. So the question is that in order to double the frequency, so F2 is double, it is twice of the first one. So F2 is equal to 2F1 over F1, which is equal to L1 over. Now, he said the length is reduced to 3/4 of the original length. It's reduced to, so we have 3/4 of L1, okay, times T2 over T1. Now F1, F1, L1, L1. So we have 2 times, when we cross multiply, we have 2 times 3 on 4 is equal to square root of T2 over T1. This is 3 on 2 is equal to root of T2 on T1. Okay, if we eliminate the square root, we have 9 on 4 is equal to T2 on T1. Therefore, T2 would be equal to 9 on 4 of T1. So, in order to double the frequency of the fundamental notes emitted by a stress string, the length is reduced to 3/4 of the original length, and the tension is changed. Then the factor by which the tension is to be changed will be 9/4. Nanama got it right. So it will be the new tension will be 9/4 of the initial tension. So only Nanama got this right. Please, is there any question? All right. In fact, I thought this would be a very last question, but I just saw one interesting question which I want you to smell. Just smell and perhaps taste. So listen. As for this will be the very last question. A second harmonic has to be generated in a string of length L. A second harmonic has to be generated in a string of length L stretched between two rigid supports. Stretched between two rigid supports. The point where the string has to be plugged is, so a second harmonic has to be generated in a string of length L stretched between two rigid supports. The point where the string has to be plugged is, or where must the string be plugged in order to obtain the second harmonic? Over to you. A second harmonic has to be generated in a string of length L, stretched between two rigid supports. The point where the string has to be plugged is, so basically, where must the string be plugged in order to generate this second harmonic? That's the question. You can test your answer. If you are done, you can test your answer. Josephine, what have you had? Somebody has tweeted. Gerard is tweeting. Okay. Gerard, I've seen your answer. Who else? Equia Adoma. Equia Adoma. Okay. Josephine. Josephine. Okay, the answer is actually 1 on 4. It must be a quarter. The string must be plugged from 1/4 from one end. When we draw the loop or the note, a second harmonic, the stationary wave or the loop for the second harmonic is this. Then reflect to form this loop. So we are talking of length L. So blocking distance is equal to L over 2P. And here, the number of loops, we have 2 complete loops. So P is equal to 2. Therefore, we have L over 2 times 2, which is 1 on 4L, or quarter of. So it means it must be plugged from one end, a quarter of the length. So if, assuming the whole length is 100 centimeter, it means it must be plugged at 25 centimeter from one end. So to get these 2 loops, it means you must, from one end, plug from a distance of 25 centimeter, either from here or from here, and you have the 2 loops. Okay, that's it. The second harmonic. Please, the second harmonic, or what overtone? The
Third
second,
over.
come again.
The third overtone.
The first overtone. Okay. All right. Let's straight move to what we started last time. And I asked you to complete something. We derived the notes for the fundamental. I asked you to complete and then get me a general relation. I asked you to complete and then get me a general relation. Okay, so for open pipe, the fundamental. So if we have L length of the pipe or string, the fundamental notes formed will look like this. Then reflect to create this. Therefore, L is equal to, this is antinode, antinode. So we have half of lambda, quarter plus quarter, so half. Therefore, lambda will be equal to 2L. If lambda is equal to 2L, then this is lambda 1, the fundamental wavelength is given by 2 times the length of the tube. Okay, therefore, frequency, the fundamental frequency will be equal to V over lambda 1, which is V over 2L. And this is a fundamental frequency, or the first harmonic. Then the second possible stationary wave formed would be L length, the same length of tube. But don't forget, I said to get the wave, the stationary wave right, we use progressive wave. We use progressive wave. Now, because this end is open, we are always starting from an antinode. Antinode always starts and then ends with an antinode. Okay, so the second one will be this, and then will end here. So the reflection would equally be like this. Okay. Therefore, L will be equal to quarter, 1, 2, 3, 4. So 4 times quarter lambda, which is equal to lambda. So it means that this will be equal to the lambda 2, the wavelength which forms this loop or stationary wave will be equal to 2L divided by 2. I'm drawing a pattern. The reason for which this is divided by 1, this is divided by 2. Therefore, F2, the second harmonic or the first overtone, would also be V over lambda 2, which is V over 2L times 2. And this is 2 times F1 is this. F1. And then the last note. The last note, which is the last loop or note or stationary wave, would be, let's pick it from here. So this is the first, second would end here, and so the third must also come here. So the reflection would also be like this. So here we have 2 complete loops within. So the reflection will look like this. Therefore, L will be equal to, this is quarter, 1, 2, 3, 4, 5, 6. Let's count it again. 1, 2, 3, 4, 5, 6. So 6 lambda on 4. And this is equal to 3 on 2 lambda. Therefore, lambda 3 will be equal to 2 times L over 3. F3, the third harmonic, is equal to V over 2L times 3. And this is equal to 3 times F1. So let's draw a general pattern. Let's draw a general pattern. Then derive an expression for the nth harmonic. So F1, F2, F3. Then let's have it for Fn. F1 is equal to V on 2L. F2, we had 2 times V on 2L, which is also the same as 2F1. F3, we had 3 times V on 2L, which is also the same as 3 times F1. Therefore, Fn will be equal to n times V on 2L, which is also equal to n times F1. So this would be the frequency for the nth harmonic, the nth note or loop. Fn is equal to n times F1, where n equals number of loops or notes or harmonic or stationary wave. Okay, so we realize that for vibration or resonance in open pipe, the harmonics or the frequencies are mixture of both odd and even. So assuming if the first frequency is 100, the next will be 200, 300, 400, 500. Whereas in closed pipes, it was integral multiples of only odd harmonics. If the first is 100, the next frequency to hear is 300. The next frequency to hear 500, 700, 900. So this is a mixture of odd, even and odd, whereas in closed pipe, it's a mixture of it's only odd harmonics. And because of this, practically, because of this is the reason why sounds or notes produced by open pipe instruments is nicer to listen than. So if you hear somebody playing the flute or the harmonica, the sound produced by it, okay, sounds so nice compared to closed instruments such as trumpets, okay, and those closed instruments. And it is because of this order of. So when the sound is produced, the first frequency you hear is in that orderly 100, 200, 300, 400 for open pipes. Whereas for closed pipe, the frequencies there are breaks. 100, the next you hear 300. In that order. It is because of this theory, the reason for which sounds produced by these instruments vary in that nature. Please, any question? All right, so do not forget that, please, in closed pipes and this one, the velocity of sound is not related to T over mu. This is applied only in stretch wise, where there's a tension. This is just blowing air into the pipe, and the air blown disturbs the frequency, natural frequency of vibration of the air column. And where they match, they resonate. Okay. And when they resonate, it creates that sound we hear. So playing musical instrument, guitar, keyboard, flute, what you hear is as a result of resonance. Resonance in sound is a situation where one object vibrating at its natural frequency affecting the frequency of vibration of another. So as I speak, you could hear my sound due to resonance. Okay, when I talk, the energy from my body vibrates my vocal cord, and then the vibration of the vocal cord also disturbs the air column within my throat and then the air. So when the air molecules within the throat and then around the mouth picks the frequency of vibration of my vocal cords, they resonate. Okay, they resonate, and every resonance is characterized by production of loud sound. So the sound you hear from me is as a result of resonance. The reason for which we term this vibration in pipes and then strength as pipes, and then whether closed or open as resonance, because they produce sound, and the sound heard is as a result of resonance. Please, any question? Any question? Okay. I want us to apply this in solving a problem. So listen to this first question, then we move on. A closed pipe and an open pipe have their first overtones identical in frequency. Their lengths are in a ratio of what? A closed pipe and an open pipe have their first overtones identical in frequency.
Mr. Dia,
Hello.
please can you start over again? Sorry.
That is important to ask. So listen. A closed pipe and an open pipe and send the question to the group. Okay. You let me send it to the group. I'm February. Okay,
Hello,
so
sir.
I've sent the question to the group.
Please, please, would you mind reading the question to me?
Okay, so a closed pipe and an open pipe have their first overtones identical in frequency. Their lengths are in the ratio. You are given 4 options. Please, we are answering the question 3. Question 3. A closed pipe and an open pipe have their first overtones identical in frequency. Their lengths are in the ratio. So let's try question 3. When you finish, we'll look at question 2 and 4. As for question 4, it's not calculation based, so we'll only discuss. But you finish with 3, and then we look at question 2. So we are just applying the theory length, whatever we saw from the concepts in answering the question. So just apply the concepts, what we mean by the first overtone in both close and open. Okay. We are told that their frequencies are identical, meaning they have some identity. It does not mean they are the same. Oh. Okay, Josephine, this is correct. So the verdict is out. Equia what ma equia doma.
Say I go 1024.
Okay. So the answer is actually 1024. But let's go through the code. So a tube closed at one end containing air is excited. It produces the fundamental note of frequency 512. So it's a fundamental note. So the notes would be the basic tone. Which is this. Therefore, here L is equal to quarter lambda. Therefore, F, which will be equal to V over 4L. Okay, and we are told that this is 512. Then, if the same tube is open at both ends, the fundamental frequency will be, so if the same tube, meaning the same length, this time L will be equal to half lambda. Therefore, lambda will be equal to 2L for F to be equal to V on 2L. Now, V is common to both situations. 4L by F1. Or it's even if either V or L. Okay. Meaning that with this. Okay, let me take my time and then. So V here would also be equal to 2FL. So if we equate both, and then 2FL, we realize that because it's the same length of the tube, LL will cancel out, and F2 will be equal to 4F1 over 2. Therefore, this will be 2F1. And you are given the fundamental frequency of the closed as This is 2 times, I think 514. Is that correct? 512. So if 512, then we'll have 4, 4 to 10 heads for F2. So that's the answer. Very, very, simple. Okay, so the last question to look at, question 4. Question 4 is not calculation based. Okay, it's just a test of concept. So listen to it attentively and tell me what you think, your answer. The question is saying that the first overtone in a closed pipe has a frequency. The first overtone in a closed pipe. See, I'm thinking of the first overtone of a closed pipe. Okay. So the first overtone in a closed pipe has a frequency A, same as the fundamental frequency of an open tube of same length. The first overtone in a closed pipe. So say A has the same fundamental frequency of an open tube of the same length. Is A true or false? Class, is A true or false?
That's a false statement.
Okay. That is what Gerard says.
It's actually false.
Said by Ekuya Boatema. Ekuya Doma, what do you also think? Ekuya Doma, is she here at all? Josephine, what do you think? Let's move on to the next. Oh,
I think
B says it has twice the fundamental frequency of an open tube of the same length. The first overtone in a closed pipe has a frequency B, which is twice the fundamental frequency of an open tube of the same length. True or false?
False.
That is a true statement.
So Gerard is saying it's a true statement. Ekuya also says it's a false statement. Inshira, do you have any idea as to whether
I think it's false.
it's false? Okay, we'll see. Then the third one, same, it has frequency which is the same as that of the first overtone of an open tube of same length. The first overtone in a closed pipe has a frequency, and C is saying, which is the same as that of the first overtone of an open tube of same length. True or false?
C is false.
C is false. And then D, none of the above. So, Gerard, which of the odds are you going by?
Maybe I'm going with the one that says that the first harmonic is 2 times the fundamental frequency.
So you mean B? Akwiaboatma, which one are you going by?
Stated at D.
Inshira? Inshira?
Please, I'm not sure.
Okay, Josephine.
Mr. Again.
Mm-hmm.
Yes, I think it's D.
It's what?
Yes, I think it's D.
Okay, so the first overtone in a closed pipe has a frequency. Closed pipe has odd harmonics. So the first overtone, which is F2, will be equal to 3F1 because this has odd harmonics. Please, is that clear? Then, if we are looking at closed pipe, open pipe of the same length, its first overtone, which is F2, this one has both even and odd. So we have F1 as the fundamental, and the next harmonic is 2F1, which is the first overtone. So this is 2F1 for closed, for open. First overtone or second harmonic. This is also the first overtone, and they don't have anything in common. So the statement that same as the fundamental frequency of open, okay, for open pipe, the fundamental frequency is F1. So A is out, totally out. It has twice the fundamental frequency of an open tube of same length. The fundamental frequency of open tube is actually, oh, okay, look at it. Oh, this is open tube. Okay, and said twice. So B is also out. Okay, it has twice the fundamental frequency of an open tube of same length. But this is not twice, this is 3. So B is also out. Then C, it has same its frequency is same as that of the first overtone of an open tube of the same, which is not true. So D, none of the above is the correct option. None of the above is actually the correct option. All right, please, is there any question? All right, let's look at end correction. What do we mean by end correction? End correction for both closed and open pipes. Now, if you take your pen, and then you remove this from it, you remove this from it, and then blow air through it, you realize that whilst you blow air through it, you also feel the reflection of the air blown into it around your mouth. here you must remove both ends because you are blowing air and so will disturb the air column within. But you feel that whether closed or open, you also feel a reflection of the air you blow around your mouth. What it means is that when the stationary wave is created, whether closed or open, let's use the fundamental. The stationary wave formed does not exactly fit the length of the tube. It does not exactly fill the length. This is the whole length of the tube. But the note created goes beyond the boundary of the tube and extend outside it a little bit. It does not exactly end at the end of the tube, but it goes beyond it a little bit. This is the reason why when the air is blown, you could feel a reflection of the very air, okay, which creates a stationary wave outside around your mouth. Meaning the notes created goes beyond the length of the tube a little bit. This is what we are referring to as the end correction. The end correction. Now, in some questions, they take note of the end correction. They consider, questions can be said where the end correction is considered or the note directly fits within the tube or the pipe. So it is either end correction E, that is how the extension of the note beyond the boundary E, what is here is the same as what is here. Or the question can be given where the note directly fits into the L length. So if it is given as such, how do we cater for end correction? If it is given as this, whatever entails in here is what we have discussed. But if there is a consideration for end correction E, how do we factor it here? Now, for closed pipe, because only one end is open, we'll only have one end correction created at the open end. For open pipes, because both ends are open, we'll have end correction at both ends. So, example, for the fundamental, you have a consideration for end correction like this. Where the note extends a little bit beyond the periphery of the tube. So small end correction E at both open ends. So in open ends, we have two end corrections, whereas in closed pipes, we have only one end correction. Please, is there any question? Okay. So if there is the need for end correction, then still for the fundamental notes, the wavelength is still quarter lambda, node to antinode, so it's still quarter lambda. So the wavelength is equal to the length of the tube plus the small n correction. Please, it is wrong to say that the length of the tube is equal to the wavelength plus n correction. This is wrong because you see the wave or the stationary wave is longer, a little bit longer than the length. So it is the length plus that little n correction, which is equal to the wavelength. The wavelength is the whole of this, starting from the close end to where the stationary wave is going beyond its open end. So it is the wavelength, which is equal to L plus the n correction and not this. So take note. So if there is a consideration for n correction, then we can say that lambda is equal to 4 times L plus E for lambda 1. Therefore, F1, which is equal to V over lambda 1, would be equal to V over 4L plus E. Don't forget, if there is no n correction, the fundamental frequency is V over 4L. So this is the difference when we are taking account of n correction. Okay, for the fundamental notes. If it's about the second note or loop or second harmonic, the same. We take account of n correction. But for fundamental notes, this is how the frequency would be when we are considering n correction. And this is the frequency without n correction. Let's look at it for open pipe. And there is a consideration for n correction. So the wavelength, this is quarter plus quarter. So half lambda would be equal to, yeah, this is the length of the pipe, L. So half lambda is equal to L plus n correction here, 2E. Therefore, lambda 1 is equal to 2 times L plus 2E. F1 for open, when there is a consideration for n correction, and this is equal to V over 2L plus 2E. Don't forget, if there is no n correction, without n correction, F1 is equal to V over 2L. With n correction, this is it. Class, is there any question?
No, sir.
So let's look at it for the second note, the second harmonic. And if there is n correction, the second note, if there for both, if there is n correction, So the second harmonic or note or the loop would be so when the stationary wave goes beyond the boundary a little bit, E. Please, we pick it for only one because what the extension here is equal to the extension here. So it means this is the length of the tube, L. So 1, 2, 3. 3 lambda on 4 is equal to L plus E. Therefore, lambda is equal to 4 times L plus E over 3. And F2 in this case, which is V on lambda 2, will be equal to V over 4L plus E times 3. So still we have, even for considering end correction, we still have F2 equal to 3 times F1, the odd harmonics also showing up. Then for open ends, for open tubes, the second note or second harmonic, when there is a consideration for end correction, would also be of both end corrections, but the wavelength, which is 1, 2, 3, 4, 4 times quarter lambda will be equal to L plus 2E. Therefore, lambda 2 is equal to L plus 2E. F2 therefore is V on lambda 2, and we have V over L plus 2E. Okay. Where this can also be expressed as 2V on 2L plus 2E. And because in the first harmonic, we had F1 to be equal to V over 2L plus 2E, we can also deduce that this is F2 is equal to 2 times F1 to follow the same trend, okay, with when there is end correction or without end correction. So this is the whole concept of end correction, meaning in each question, if there is a consideration for end correction, you must take account of it. I'll look for questions on end corrections and then give it to you appropriately. Please, is there any question?
No, sir. No, sir.
The girls, you are not talking. Is there any question?
No, please.
Okay. Let's quickly look at the resonance tube. The resonance tube. So we have to finish this and then quickly by next week and then start a new topic. The resonance tube. As usual, I'll look for questions on this so we can apply. Now we have what we call the resonance tube experiment. The resonance tube experiment. And the resonance tube experiment is actually an experiment that is used to determine the velocity of sound in air using a tuning fork. So the resonance tube experiment is an experiment that is used to determine the velocity of sound in air using a tuning fork. A tuning fork. What is a tuning fork? A tuning fork is a device which looks like the fork we use. We have tuning forks in the laboratory. I think I'll look for one and then show it to you next week. The tuning fork it's used to generate waves. Okay, it's used to generate waves. But one peculiar characteristic of the tuning fork is that it produces a wave with a fixed frequency. So the tuning fork is a device that is used to generate wave of a fixed frequency. Okay, and this is because the tuning fork has a fixed frequency. A fixed frequency. So because the tuning fork has a fixed frequency, that is the reason why it is also used to generate a wave with a fixed frequency. Okay. Now, the resonance tube operates on the principle of the resonance tube operates on the principle of closed tubes or pipes. So that is the principle on which it works. It works on the principle of closed pipes or tube. And we've just gone through the principle of the closed pipe. In closed pipe, one end of the pipe is closed and one end of the pipe is open. So here, the resonance tube experiment, we use the burette. The burette you use in your chemistry titration. We use it because the burette is such that one end is closed and the other end is open. So we use the burette, fill it with water or any other liquid. Okay. And then create a tap where the water within the burette can be regulated. Then the tuning fork, okay, is used to strike a rubber band to generate the wave. And then the wave generated is brought close to the open end so that we create a stationary wave within the burette. Okay, so I'll end it here, and then next week we'll look at whatever goes into it and consider the calculations involved. Then from there we can generate the velocity of sound in air. I said it is an experiment that is used to determine the velocity of sound in air. So we'll go through this, how it is applied to determine the velocity of sound in air. This year, I think practicals in Alt B, they had a practical on resonance tube experiment. So we'll use the theory to also answer the practicals, meaning we'll be doing the practicals without touching any device, but we'll actually apply our understanding of the theory to do it. Okay, so this is the whole stuff, or maybe 80% stuff about the resonance tube experiment. Please, if you have any question, ask. If there is no question, then we end today's show. Okay, is there any question? All right, then this is where we end today's meeting. Good night to all of you. We'll continue next week. Bye-bye.
Good night, Mr.
Yeah.
Bye.
Okay.